about the formation of acetals, and then a little bit later on we'll talk about the hydrolysis of acetals. So this is the first part, is the formation of acetals, and here's the overall picture of it. We start with an aldehyde or a ketone. The aldehyde has the H at the end. The ketone has carbons on either side. So that's why R there stands for rest of molecule. The aldehyde or ketone is reacted with a different kind of alcohol. This is just generic ROH in the presence of sulfuric acid. It is a equilibrium reaction. So in the first step, the alcohol is added across the double bond. And so you get a hydrogen to one side and the ethoxy or the methoxy, the ether group on the other side. So that's what where the ROH comes from. That is the hemiacetal. It is a hemiacetal because you have an alcohol and an ether group on the same carbon. That reacts further with another molecule of alcohol in the presence of sulfuric acid to give the acetal, which has two ether groups coming off of the same carbon atom. Water is a byproduct of this, which is why we can push the equilibrium backwards when we hydrolyze acetals and hemiacetals, coming up in a little bit. All right, so let's get into some examples. So the first thing I would recommend doing is analyzing what you got. So we look at this molecule and we see this carbon right here. We have an ether group on this side, and in particular this is an ethoxy group. It is ethoxy because we have two carbons, and two carbons is eth. Then we also have an alcohol group. That alcohol group is right there. So this is a hemiacetal. We're going to take the hemiacetal and react it with methanol. I'm going to color that one in red. Here we go. This is methanol. I'm going to just abbreviate it with MEOH. Me stands for meth. CH3 is a one carbon group, and so that is methanol. So the hemiacetal is going to react with methanol in the presence of sulfuric acid to form the acetal. So we're going to keep the carbon skeleton. Everything there is the same, and the alcohol group gets transformed into the methoxy group. So you can write it like that with the OME if that is easy for you. That is exactly equivalent to carrying out with the CH3 group coming off of it. You can see we didn't change the carbon skeleton. All we added was the methoxy instead of the hydroxy. There still are acetal carbon. The byproduct of this is water. So that's the first, or that's the reaction of a hemiacetal with an alcohol in the presence of sulfuric acid to give the full acetal. Next up, we have, I'm going to show you this in the two steps. First off, analyze what you have in the reactants. This is a ketone. It's a ketone because you have a carbonyl with carbons on either side. I'm going to name this because I care about nomenclature. We number it to give the carbonyl the lowest number that we can, so that carbonyl is at carbon number 2. We have a methyl group at carbon number 3, so this guy is 3-methyl 2-butanone. But because it's a 4-carbon chain. 2 because that's where the ketone is located, and 3-methyl because we have a branch at carbon number 3. That is going to be reacted with ethanol, which is CH3CH2OH. It's just a shorthand way of writing it. And we're going to react it in the first step to form a hemiacetal. And then the hemiacetal is going to react with another molecule of ethanol to yield the acetal. So I'm just drawing it in two separate steps. The most important thing that I'm going to tell you to keep in mind is to keep the carbon skeleton the same. It's the same over here too. The carbon skeleton doesn't change. It's really hard to break carbon-carbon bonds. It's really, since it's hard to do it, you need really specialized reaction conditions to break carbon-carbon bonds. So you don't do it very often. So we're going to keep that carbon skeleton the same. We're going to zoom in here. Carbon number 2, that's that carbonyl carbon. that's going to be the carbon where all of our action is going to take place. So in the first step, we're going to add the alcohol group across the double bond. So we're going to keep the oxygen that is in our original molecule, and a hydrogen goes with it. There's our alcohol group on the hemiacetal. And then over here, we form a bond to the OET. So you can see where all of our parts of ethanol go. The hydrogen goes to the alcohol, the O that was the original ketone alcohol. And then the ETO goes to the other side. So that's the formation of the hemiacetal. Then that's going to react one step further. That reacts to form the full acetal. The OH goes away and it gets transformed into the OET. Water is the byproduct of the reaction. So that is the acetal that is formed. Those are the straightforward ones. The next two are going to be a little bit trickier because these are this is straightforward because there's no rings. So you know it's coming. Here's the reaction of an aldehyde. This is an aldehyde because you have that hydrogen on the side there. So that's what makes it into the aldehyde. And we're going to react that aldehyde with a diol, because it has two alcohol groups on it. Just for funsies, because I care about nomenclature, let's name this aldehyde. 4 carbons in the chain, that means it is a bute, and it is an aldehyde, so that is butanal. The AL ending is the aldehyde ending, so that is butanal. We're going to react it with that diol. I'm going to show it in 2 steps, but this, you can tell it's going to be a ring because our alcohol is bifunctional. Bifunctional means it has 2 functional groups in it. Now, not every single bifunctional group, 2 functional groups, not every single bifunctional molecule is going to form rings. But it's definitely something that you can think to yourself, like, oh, okay, I've got 2 functional groups present. There's the possibility for a ring to form. All right, so first step, we're going to add the alcohol group across the double bond, just like we did in the previous ones. Add one of the alcohol groups across the double bond. Keep the carbon skeleton the same. 1, 2, 3, 4. Keep the carbon skeleton the same. It's not easy to change. When you add the alcohol group across the double bond, you form an alcohol and the ether. I'm going to number this. So we have the O, and then we have 1, 2, 3, and then another O. O, then 1, 2, 3, and then the OH. That's the first step. It's ugly, but just keep going with it. This is the hemiacetal. It's a hemiacetal because, just one second. It's the hemiacetal because that carbon there, the acetal carbon, is bonded to an alcohol group to the left and an ether group to the right. Now, this molecule is going to react with another molecule of alcohol to form the acetal. The difference between this and the other reactions is that this has the alcohol in it already. So this guy is going to swing on over and form a ring. The most important thing, okay, again, keep the carbon skeleton the same. I can't emphasize that enough. Don't change carbon skeletons. We know we're going to have up to the O, and then we have 1, 2, 3, 1, 2, 3, then to another O, and that comes on down. So this is the acetal that is formed. The other alcohol to form the acetal is already tethered to it. This alcohol group is tethered. It's bonded into the molecule. And so that's how you form the ring. So that is a cyclic acetal formed from an aldehyde. One more example of this. This is another tricky one. This is a tricky one because you have another bifunctional molecule. You have an aldehyde, you have an alcohol, but they are tethered together. This alcohol group is going to swing on over to bond in to the carbonyl carbon. In my opinion, the best way to do this is to figure out how big your ring is going to be. It's going to be a 6-membered ring where the 6th member is an oxygen. So let me redraw it swung around. There's the aldehyde. 1, 2, 3, 4, 5, and 6. And that 6th member of the ring is the alcohol. Don't lose your substituents. At carbon number 3, you have 2 methyl groups. So now this O is going to swing on over and click right into that aldehyde. You're going to form the hemiacetal. The hemiacetal is an alcohol and an ether. I didn't really leave myself enough room, so I'm going to draw it down here. There's our alcohol. There's the rest of the molecule that is the ether. That is the hemi. This is a cyclic hemiacetal. Why is this important? For carbohydrates. And we'll get to there when we get to biochemistry, but hemiacetals are all over the place in saccharides, monosaccharides, disaccharides, in carbohydrate formation. Now this hemiacetal is going to react with the methanol to form the full acetal. That full acetal now looks like this, where the alcohol group has been transformed. So we have this carbonyl carbon is the same in every case. That's the acetal carbon. That's where all of the stuff is happening. And the hemiacetal is alcohol ether, and the full cyclic acetal is ether ether. So you've got the methoxy group, and you've got another alkoxy group, the ether group going on. So that is the cyclic acetal that's formed. Now, I think that this next part is easier. All right, we're going to push the acetals to break back down. So everything is in equilibrium. So we can use Le Chatelier's principle to force these equilibriums back to the original. So how that happens, you can start with an acetal or a hemiacetal, quite frankly. This is showing it with acetals, but you can do it with a hemiacetal as well. If you flood the reaction with as much water as humanly possible, that's going to push the equilibrium, for this one, the way it's written to the right. You're going to hydrolyze it. Lysis means breaking. Hydrolysis means breaking bonds with water. Breaking bonds with water. So really, the shortcut way of doing this is all you got to do is recognize that this carbon in particular, that's going to be your carbonyl carbon. You cut off the alkoxy groups and shove in a carbonyl group. And that is it. Cut off the acetal groups, cut off those ether groups, and turn that acetal carbon back into a ketone or an aldehyde. Give it back its carbonyl. And that is as straightforward as hydrolysis goes. So let's take a look at this one. And I'm not going to go stepwise. I'm going to go just full on all the way back to the carbonyl containing compound. We are flooding this with tons and tons and tons of water. Again, you'll hear me say it a lot. Keep the carbon skeleton the same. So all of those carbons, they are still absolutely bonded to one another. Don't lose your carbon skeleton. Zoom in here. That's the carbonyl carbon. That's the acetal carbon. So that's over here in this molecule and the product right there. You're going to cut that off. We don't want that ether group on there. We don't want that ether group on there. You just turn it into a ketone. I'm going to name it because, again, I care about nomenclature. So this is a ketone. You got a ketone at carbon number 2. You have a methyl substituent at carbon number 4. So this is 4-methyl 2-pentanone. Oh, my pen. There we go. Pent because there's 5 carbons in the chain. 2 because the ketone is at carbon number 2. 4-methyl because you have a 1-carbon substituent coming off of the chain. So really, all you do, figure out where that acetal carbon is. When you go backwards, when you flood it with a ton of water, you push it back to the carbonyl containing compound. So you just axe out the ether groups, shove a carbonyl in there. Let's take another look at it. Let's take a look at another example rather. This is a hemiacetal. You know it's a hemiacetal because you have an alcohol group and the ether group. So you have a methoxy and an alcohol. We're pushing it backwards. We're flooding it with water. That means that this is going to undergo hydrolysis, breaking bonds with water. So keep the oh, that's not what I wanted. Let me make that narrow. I'm sorry, guys. Keep the carbon skeleton the same. And I'm just putting that H there just for fun because it's in my original molecule. So keep the carbon skeleton the same. Zoom in on the acetal carbon. Axe out your ether, and in this case your alcohol, and put on in a ketone or a carbonyl compound. This one in particular here is an aldehyde. It's an aldehyde because it ends with an H. So then nomenclature, this is butanal because it's an aldehyde and there are 4 carbons in the chain. So just find that acetal carbon, pull off the alcohol and or ethers, put the double bond to the oxygen in. That's how you hydrolyze. Let's look at another example. Again, we're going to get trickier because here's a ring, but everything's the same. Find the acetal. The acetal carbon is the carbon that is bonded to the 2 O's. So that's the acetal carbon. Keep the carbon skeleton the same. Find the acetal carbon in the product, and throw on the ketone. Or throw on the carbonyl. I'm sorry, I keep saying that. Throw on the carbonyl compound. And in this case, the carbonyl compound is an aldehyde. It's an aldehyde because there's an H to the one side. The alcohol group in this case is interesting because it's cyclic. So the alcohol group that we're pulling off is the diol. You can see that here. Let me color code it. I'll color it in green. There's our alcohol group that we had to put on. So you can see how you can go back and forth. When you have that bifunctional alcohol, that's going to form the cyclic acetal. So when you undo the reaction, when you hydrolyze the cyclic acetal, you end, in this case, with an aldehyde and the bifunctional diol. All right, so you know what's coming next. Another cycle. This one's even trickier, but it all follows the same principle. Find the acetal carbon. The acetal carbon is the one that is bonded to both O's. Then you're going to break the bond to both of them. And you're going to stick a carbonyl on there. Now, this one's tricky. I'm going to draw it kind of funky, and then I'll draw it where it looks a little bit better. All right. We broke a bond, but everything else is staying connected. We're going to take that acetal carbon, that's still the one that's right there, turn it into its carbonyl, but then we have to make that into the alcohol. That's all there is to it. The other product of this reaction is the ethyl alcohol. So let me try to color code this so you can see where we're going. There's the other alcohol group. Sorry, let me make this blue color. There's the oxygen there, and that hydrogen is one of those hydrogens is coming from the water. And that's how you do it. You find the acetal carbon, you cut the bonds to both oxygens, and you shove on a carbonyl. The only difference is when it is cyclic like this, it's going to be bonded together. That is that bifunctional molecule. I'm going to draw it out nice and straight so y'all can see what's happening. It's 5 carbons, aldehyde at one end. 1, 2, 3, 4, 5 carbons with an aldehyde and an alcohol. So you can see how that can go forward to form the cyclic hemiacetal, and how now we can push it backwards to form the aldehyde and alcohol combination. So it's bifunctional. So again, whenever there are rings, you can think about it being bifunctional. It's not always, but it absolutely is something that you can think about in your head. So that is the formation of acetals, and then the hydrolysis of acetals to form carbonyl-containing compounds, either aldehydes or ketones.